Hello, my name is Al Chambers. I'm a senior applications technologist here with BASF at our Mount Olive or Bud Lake facility here in New Jersey. Thank you for joining us. Today, I hope to spend just a little bit of time to discuss UV weathering and the resistance of polymers to UV weathering and how we go about accomplishing that, what type of equipment we use, and how that equipment functions. At the end of the presentation on UV weathering, we'll do a small basic touching on the UV stability, particularly of nylons, which is what this presentation is kind of geared around. As far as the UV weathering section of this, although it's geared toward automotive and some of your lawn and power equipment type operations, the type of testing done and the procedures that are utilized to do that apply to just about any molded polymer, whether it be nylon or in the polyolefin type of polymer. As I mentioned in the beginning, we were going to discuss weathering and why it is important to do it. As you can see by this slide, some of the things that affect polymer or a molded product that we refer to as weathering, and we try to simulate these type of exposures, just exactly what their effect is on a molded polymer, depending upon what its application is and just exactly what is expected of that particular part or polymer. Particularly in weathering plastic materials, the things that we really look for as to be affected is, of course, the color and color shift, particularly if it's something other than black. The gloss retention of the finished part, as everyone knows, as retention is lost, particularly in molded products, the surface aesthetics become unpleasing. So this is another thing that is monitored during weathering of polymers, as well as one of the most important things, of course, is mechanical properties and how they stand up and meet the requirements of the application. We do weathering in two basic phases. There's accelerated weathering, which we do because in most instances a application cannot wait for something like this natural weathering to be accomplished because it takes such a long time. We do accelerated in conjunction with the natural weathering. Here is explained the natural weathering and in most cases where it's accomplished. We use the two climates that are listed here. Of course, Arizona for hot and dry, Florida for hot and humid, and in some cases salt atmosphere type things. And as this weathering is accomplished, we monitor the effects that it takes upon either a part that we actually mold or on a part that is supplied by the end user or the customer. So the things that are generally monitored and how they are monitored in natural type applications are basically pretty much the same thing that we do on accelerated. We look for properties deterioration, loss of gloss. In a lot of cases, we look for surface degradation, cracks, crevices that appear as a polymer is affected by degradation. Impact modified grades are particularly susceptible to this because in most cases, impact modifiers are on usually some kind of a rubber base that during heating and cooling, they tend to break down. And so these are some of the things that are monitored, not only in accelerated weathering, but also in natural weathering. This little sketch here shows some of the difference in the major regions. They're kind of spelled out by the color codes. As you can see, the hotter climates, of course, are generally the real red areas. The moderate climates are those with the orange. The climates that change readily are the greens and grays, and the really cold climates, of course, are designated there as the purplish shade. This graph here kind of illustrates some of the multiple areas that weather testing is done, and it's done in these areas primarily because there's such a wide variation in exactly what it's going to see. And as you can see, some of the vendors that are utilized to do this kind of weathering are located just about all around the world and in multiple different type climates. This particular slide here breaks down the general three criteria that are utilized for accelerated type weathering. The two that are listed there as SAEs are automotive specifications, is an interior type test to simulate the type of effects that are seen by a polymer on the interior of a vehicle. The other one listed here is just the opposite, that is to simulate the type of effects that a polymer will see as an exterior application. The other one is an ASTM. This is a standard that is utilized primarily by the power tool and lawn and power equipment manufacturers, and it also in some cases covers office furniture and other things that do not see the severe type things that automotives see. It's a wide specification that covers multiple type applications and different test methods under the G-type. A quick overview of the protocol, the test protocol. As I mentioned, this is an interior test, so there's no water involved in this test, and it's done at a somewhat higher temperature than you would see on the exterior of an automobile, due to the fact that heat does build up in the interior, so it's run at a higher temperature than that of the exterior. And it's also done at a shorter duration. There is a certain amount of UV filtering being done by the auto glass itself. In some cases, there's additives added to interior applications to try and negate or minimize the effect of this high heat and sunlight in the interior of a vehicle. This little overview here explains the exterior application, and as you can see, this one is done in a wet-dry to simulate not only rain but acid rain, and it's done at a much longer duration than that of the interior, because you can gather the necessary results for an interior. If failure is going to occur, it's going to occur rather quickly. On the exterior, if failure is going to occur, it might take over a much longer period of time. So this test is not quite as hot as the interior test, but it is a wet-dry test. I like to reiterate that exterior applications, particular mirror housings and roof racks, they suffer what I refer to as thermal shock. In other words, they're brought up to an extremely high temperature and then they're hit with a cold water spray. And this causes what I refer to as thermal shock, which can propagate the cracking and crazing of the surface, as I mentioned before. As I mentioned earlier, this presentation was generated and programmed around nylon 6 type product, but the test methods, criteria for and necessity for doing this type testing pertains to just about every polymer, not only just nylon. But in this case, we're talking about nylon, and some of the reasons why we do this weathering is to screen out the necessity for improvement, whether it be stabilization type improvement to improve properties, or whether it be some kind of an improvement, improved color retention. The two biggest facets that are looked at by the end-use customer: surface aesthetics, color, and properties. And as I mentioned at the beginning, I was going to touch on just exactly why we use accelerated weathering as compared to natural weathering. As I mentioned, most programs and applications need to be launched and launched very quickly, so that we can't take the extended period of time that it takes in order to facilitate natural exterior weathering, which in some cases can be a couple of years or longer. So we try to simulate those effects in an accelerated method by using artificial type representations of wavelengths of different irradiance and UV exposure. And that's done on an accelerated basis. Like this slide kind of touches on, the reasons for doing that is just to get the product out there and do the natural weathering to validate that the accelerated weathering gave you the data that's necessary. There's basically three different setups that we use for UV exposure, and it more or less depends upon what the end application is and what the requirements of the customer and the application are. As you can see, UVA is one of the relatively mild exposure parameters. If you wanted to kind of relate this to something, this is the kind of exposure that you would expect yourself to be exposed to that would cause possibly a suntan, but not a sunburn. And then as you get lower in the UV exposure range, the next range would be a much shorter wavelength, which makes it much more severe. This is the kind of exposure that would cause a sunburn. Here on the surface of the Earth, you will never see anything below that 280 nanometer wavelength. This is the sunlight you would see outside of our atmosphere. Our atmosphere filters out a certain amount of UV exposure, otherwise man could not live here. The range that we generally test in, anywhere between 300 to 315 up to 400. Generally, we don't go below 300. We can set up equipment to test at that wavelength and that irradiance, but it's not realistic unless it's an application that is more or less atmosphere or stratosphere. This graph here shows a relative span of irradiance or wavelength. As you can see, this area in here is the area that we deal with for UV protection. And this area in here is the small area within the overall that the human eye can actually detect color in. So as you can see below this area, you go from like a bluish or purplish that the human eye can see, and you drift into ultraviolet. At the other end of it, out at this end, you drift from the extreme reds and you drift into infrared. But it's within the whole realm of things, all of this is very, very, very small. And this is just about one of the smallest of all. This chart here depicts in wavelength what the difference is. Now, as you can see, this yellow line that runs through this area is the actual wavelength that is thrown by the sun. And all of these others are types of equipment that are utilized to try and simulate as close as possible to that wavelength of the sun. And as you can see, the one that is probably the closest is this red line, which simulates xenon arc. And that is the method that is most commonly used for UV testing. On this slide here, we kind of address some of the reasons and some of the criteria that should be considered when you request or you feel that you need UV weathering to be done on a product. A lot of products, because of their application and the expectations of their performance, no UV type testing or accelerated testing are done on these. These are applications where they never see this kind of exposure, so it's not really necessary. So you always must consider, do I need to do this because it's not really cheap to do? And if I do need to do it, just exactly what kind of conditions and so forth should we be looking at, and what are the end results that we expect? These three things listed here are the most important things that you want to consider if something is going to see a tremendous amount of light. And I don't mean artificial light. It has to be sunlight or reflected sunlight. Is it going to see extreme high temperatures? And is it going to see a lot of humidity and moisture that might have an effect upon its performance? You consider these things. If none of these three things come into effect, then it's quite probable that there is no real necessity to spend the time, the money to do accelerated or even natural weathering. As I mentioned before, there's some things that have a tremendous effect upon the performance of just any polymer, not only nylon. I'm going to touch on a couple of those. Radiant energy, this is the extremely harmful protons and electromagnetic waves that the sun radiates. A good percentage of are filtered out by our atmosphere. And then you've got total irradiance, which is a combination of all of those exposures, and it's expressed in a watts by meter squared type of equation. It's important that you understand radiant and irradiance and specular irradiance, because these are the things that factor into the total performance of your end-use product. They're not really necessary that you totally understand what the formulations mean. It's all calculated and computed automatically, and the results are given to you in a numerical fashion. We're kind of getting into just exactly what is involved in the equipment that is utilized to come up with the results of accelerated weathering. Some of the components of the equipment that is utilized we'll touch on here, and then I'll show you a picture of the equipment and apparatus that is utilized to get these end results. Within this unit is what is called a black panel sensor. What this panel does It regulates the equipment to make sure that you stay within the temperature range that you've set it for. So if you've set it for 87 degrees C, plus or minus 1 degree or so, we'll shut the equipment down so that you do not run outside of the expected parameters. So this particular part of the unit controls the temperature. And you've got a light source. I'll show you this in the design itself a little bit later. But the light source is a water-cooled xenon lamp. You can obtain different wavelengths that we had looked at here before by changing different filter combinations. Because on this xenon lamp, you've got an inner filter and an outer filter. And between those two glass filters is water. And that's deionized water that is used to keep those filters cool because of the high heat that is given off by the light source. As it's mentioned here, these units are calibrated weekly depending upon the cycle that they're set up on. We'll touch on that a little bit later, but the J1885 type thing is a 4-day cycle, where the J1960 is a 6-day cycle. And at the end of each one of those cycles, all of your specimens are removed from the equipment. They're observed for surface degradation, and spectrophotometer or color readings are made on them after each cycle. The unit itself is then calibrated. The samples are relocated back into their holders and put back into the chamber, and the next cycle starts. This is just a little reinforcement of what we had talked about before on the two automotive specifications and the apparatus that is used. And as you can see, it's set up at 0.55 watts per meter squared, which is your total irradiance. And it's run at roughly 340 nanometers, which is somewhere just around mid-range that I told you we test in, which ranges from 300 to 400. So this is about mid-range. It's severe, but it's not overly severe. Just recently, within the last 18 months to 2 years, Ford Motor Company has come up with a new test criteria. It's still based on a test protocol. The only difference is where we used to use a borosilicate inner and a quartz outer, now they have changed it to using a borosilicate inner and a borosilicate outer. Therefore, they came up with Bora Bora. The test itself, the irradiance is a little bit softer, not quite as harsh, but they've changed the duration of the test from 2,000 hours to 3,000 hours, or 2,500 kilojoules to 3,900. So the length of the test is much longer, but the severity is not quite as severe as the original J1960. And as I mentioned before, we would touch on just exactly what these cycles are. Now, I tell you that this test here is a 6-day cycle, and each evolution within that cycle amounts to 3 hours. Those 3 hours are 120 minutes, like it says, of light, and then 60 minutes of dark. And then there's also a water spray on the front and a water spray on the back of the specimens, and I'll show you how that's accomplished when we get to the diagram. The 1885, I told you, was not quite as severe. This only runs 4-day cycle. Each segment inside of that cycle is 3.8 hours, where there's light from the light source from the xenon lamp, and then 1 hour of darkness, and then the cycle repeats. And this continues on for 4 days, and then the equipment shuts down for readings and recalibration. So on an overall basis, comparing interior to exterior, as you can see here on the interior, of course, there's no water spray unless somebody's playing with a water gun in your car, but it's at a higher temperature to simulate the rise in temperature that you experience on the interior of the car when it's all closed up. The exterior is with water spray and a little bit cooler temperature, as you can see here. This test protocol here is an ASTM protocol. This is a test protocol that is generally used for power tools, whether they be electric or whether they be remote or battery-powered hand tools, lawnmower decks, tractors, those things that see some exposure to the exterior, but not as severe as an automobile, because most of the times the things that are tested under this test protocol spend some time outside, but in most cases are stored where they don't have exposure to sunlight and the elements. Things that are tested under this test protocol is a two-phase type test. Both tests are done for 1,000 hours, but one test you're looking for the properties retention after exposure. In that test, it is a wet-dry test for 1,000 hours. Then the second phase of it is for color retention, and that's also 1,000-hour duration, but it's totally dry. There's no water spray. This is done in the same type of equipment, only set up at a different test protocol. I'm not going to try and read any of these. You can take a look at them later if you want, but these are just a couple of slides to show you examples of what that test protocol is. They spell out the type of apparatus that they want utilized for the test, and they also list the method, and they'll also list to you how to report your results. This diagram is the interior of one of these accelerated weathering chambers. This little unit right here is a photoelectric cell which picks up the radiance or the light given off by this, which is your light source. This is the xenon lamp in the middle. And the light given off by that is picked up by this photoelectric cell, and it regulates to make sure that it stays within its proper radiance. Back in this area here is where the black panel is. And the black panel makes sure that you do not go outside of the heat and light settings that you programmed into this particular test. These nozzles here supply the inside and outside water spray. On these racks that I'm pointing out here is where the specimens are held. Up in this little box up here is a piece of gray fabric with a probe within that fabric, and what that does is controls the humidity and the moisture inside of the unit. And as you can see, it's all mounted on a pedestal down here at the bottom, and this unit rotates. That's the interior of the unit. This shows the exterior of the unit. And the technician here, in his hand, he has one of the test specimen holders. These are the holders that are most utilized and the easiest to work with, although you can actually mount actual molded parts inside of the unit. Doesn't give you as good a results if you have an actual molded plaque that you can fit into one of these holders and mount inside of the equipment. Conventional weathering, or natural weathering, as we had mentioned before, it takes a long time to do it, but we do it in most cases in conjunction, particularly with automotive, where they want this results, but they can't wait for it. So they take the accelerated weathering results in order to launch a particular program, and then they expect this data later on to fortify just exactly what they can expect as far as performance of these applications 2, 3 to 5 years down the line on vehicles that are already out there in the field. For exterior materials, like I say, in the U.S. here, most cases it always goes to Florida, down in Miami-Dade County for exterior exposure. For interior, it generally goes to Arizona. It can be done in Florida, but it generally goes to Arizona. It's what is called black box testing for interior. All this means is that the specimens are mounted inside of a box that has a glass cover over it to more or less simulate the interior application of a vehicle. We work very closely with the folks down in Miami. Monthly, they send us a breakdown of the exposure and time of exposure that our specimens were subjected to in South Florida. This slide here shows one of the test fields down in Florida, and as you can see, all of these specimens are mounted on racks, and they're mounted at different angles to the sun, depending upon the exposure that they can expect in their final application. Generally, these are washed periodically with fresh water to rinse away the salt from the atmosphere in Florida. That simulates the fact that, of rain. And as you can see, this is a tremendously large field, and this is only one of them. The question always comes up, just exactly how do you relate what you generate as far as data accelerated to actual Florida? Is there an equation? Well, truly there isn't. What we're doing accelerated is very controlled. What is happening in Florida or Arizona is dependent upon weather shifts. What we can do is we can estimate based upon years and years of accumulated data that the general J1960 type exposure generally mimics as close as possible to approximately 2 years in Miami. But that depends upon the weather conditions in Miami over that 2-year period. We work very closely with the folks down in Miami. Monthly, they send us a breakdown of the exposure and time of exposure that our specimens were subjected to in South Florida. This slide here shows one of the test fields down in Florida, and as you can see, all of these specimens are mounted on racks, and they're mounted at different angles to the sun, depending upon the exposure that they can expect in their final application. Generally, these are washed periodically with fresh water to rinse away the salt from the atmosphere in Florida. That simulates the fact that, of rain. And as you can see, this is a tremendously large field, and this is only one of them. I told you before that one of the things that is taken into consideration during not only accelerated but natural weathering is the condition of the surface aesthetics. Best possible way to determine deterioration of the surface and loss of aesthetics is we use what is known as a gloss meter. Gloss meter is just a unit that shoots a beam of light at a certain angle to the surface of the specimen, and it bounces back and is collected on a mirror on the other side of the unit, and the amount of gloss is given as a numerical value. So we take initial gloss readings, and then after each one of the cycles that specimen goes through, we take another gloss reading, and we notarize and keep a count of loss of gloss across an entire test cycle. And this is what one of those units looks like. Some of these units have the ability to do just about all of those angles, and then some of them are set up to do one angle only. This is a list of the equipment that we have available here at Budd Lake in Mount Olive. There's 3 CI65s. That's a weatherometer that's represented by the diagram that I showed you before. We have 3 of those. 2 of them do exterior testing. 1 of them does interior. The CI5000, that's a unit that has capabilities beyond those of the CI65. So we utilize that unit to do some of the testing for furniture and power tools. That one happens to be set up for the wet part of that test, which I told you is for physical properties. Then we have a smaller CI3000. This is also set up for the G26 type testing, and this does the dry test, and that's for color retention. We have 2 QUV cabinets. These utilize fluorescent bulbs that are designed at different wavelengths. You have UV 313s, which are very severe, and then you have UV 340s, which are not quite as severe. You just change these fluorescent bulbs and you put the specimen into these QUV cabinets. QUV cabinets, almost impossible to correlate anything with a QUV cabinet to an exterior or interior exposure. What we generally use these units for is comparison. If we have a product or a specimen or a molded item or unit that we know meets the criteria, and we put something that has been developed as either a replacement or something to enhance or be better than, we can use these QUV cabinets and compare side by side to see just exactly what the performance is. That kind of wraps up the UV weathering segment. I sincerely hope that you've got something out of this to give you a better understanding of why testing is done, how it's done, and what equipment is utilized to accomplish that. I'll take just a couple of minutes now, touch on stabilization to try and enhance the stability, in this case particularly nylon, although stabilization systems apply to all polymers other than nylon. But like I say, this presentation was geared around nylon, so a couple of the stabilization systems that we touch on here will be specifically pointed at nylon 6 and nylon 6/6. The real reason for stabilization in the first place is just exactly what would happen to a polymer or a end-use molded product if no stabilization at all was utilized. And as you can see, some of those things are listed. You would most likely lose some of your physical properties, if not a good percentage of them. Your color, if there's color involved, would most likely shift as you got some degradation of the polymer, the carrier. and the surface degradation that we talked about before would most likely start to occur, particularly in nylon. In conjunction with your color shift, there would be very little protection for the colorants involved or the pigments. This screen here touches on generally how polymers are stabilized. In some cases, depending upon what the end use is, if you're looking for exterior or in some cases minor interior applications, a UP package of some sort is incorporated into the compounding of your finished product. Multiple things are used in order to accomplish this. In some cases, it's UV stabilizers themselves or radical chain inhibitors. In some cases, those might be either a organic type stabilizer or carbon black, which is one of the best radical chain inhibitors that's out there. But not like Henry Ford said, everything can't be black. In nylon, which is what we've centered around here, the most common stabilization, and it's not proprietary, everybody knows this, copper is the best known stabilizer for nylon polymers, whether they be nylon 6 or nylon 6/6. They have tremendous advantages because the cost is so very low, and the fact that it takes a minimal amount in order to accomplish the end results. They're tremendous for properties retention, particularly in high heat type applications. The disadvantages, of course, are copper halide causes a color shift in a natural polymer. It can go anywhere from a pale green to actually an amber type color. And if it's an end polymer that's a combination of more than one polymer, the other polymer involved beside the nylon just might not like copper at all, and you would get adverse reactions to the copper halide with another polymer. And of course, it's not a UV stabilizer. It's put in there as type of an antioxidant, so it doesn't truly give you real UV stability. The alternative to coppers is using antioxidants of a organic nature. Things that are used here are predominantly hindered phenols that I mentioned here, phosphonates, and organic sulfides. These perform as well as a copper halide type system. The disadvantage here, as we'll touch on in a little while, is you must go in at a higher level, and they're somewhat cost prohibitive. As far as for UV protection, which comes into case when it's an exterior type application or one of those where it's going to be exposed to either UV light or high heat and humidity, and UV resistance is one of the criteria for the end use. We use a combination of things. Carbon black, of course, is listed here as one of the best scavengers out there, but we use benzotriethols, benzophenones, and in some cases HAL, or hindered amine light stabilizers. And like I said, generally it takes a combination of these and not just one. And that's kind of explained here in this little slide that says that the combination of one or more is far superior to just one. And hitting upon that proper combination to acquire your desired results is what R&D is all about. There's a lot of combinations out there, and they perform differently depending upon the polymers involved. Now, here's the advantages and disadvantages, of course, of the organic. We touched on them slightly. You get the color protection with the copper halide system, in most cases detrimental. It protects the polymer, which reduces the yellowing. It says reduces yellowing here, but what it actually does is deters oxidation, which particularly in nylon and polyesters gives a yellowing effect. And when it says polymer protection, what it's saying there is it's protecting the physical properties. And the disadvantages, like I touched on before, is that it is more expensive. A lot of these are, a good percentage of them are low molecular weight type organic stabilizers, which in high heat or shear type applications, they might tend to try and get out of the polymer and bloom to the surface. Depending upon what other things are involved in your final polymer mix, they might interact with other additives. And as we touched on, one of the big advantages of the organic packages is color stability. It certainly slows down the degradation of color. It's very difficult to completely override the degradation of color, but the objective of the stabilizer systems is to minimize it and give it as much longevity as possible. As you see the color go, as listed here. If the color shows degradation, you can almost guarantee that you're getting some kind of polymer degradation also. In some cases, other than UV stabilizers, the HALs and the phenols, there are, in some cases, some other additives that might be added to protect primarily the color. And then there's other additives that might be added to protect primarily the resin. All of these add tremendous expense. If they have to go in at 1/4 of 1%, you're talking about adding 6 or 8 cents. So the end use really has to justify the use of some of these additives, because you can see what the cost involved in some of these, which we call sophisticated additives, will incur. So quickly, in summary of the additive section here, as you can see, copper halide, like we mentioned, is lowest in cost. It gives good performance. Its disadvantages is if it's a colored product, you most likely cannot use a copper halide because it's going to cause some discoloration. Copper halide systems are used in generally very dark and black colors, particularly if the color is one of the most important considerations of the end use. And conclusions. As we mentioned right at the beginning here, the objective of stabilization is to override that heat and light, which causes degradation of your polymer. When you have degradation of your polymer, it causes a direct result as to the performance of your end use. And the objective of these, although they add a little cost, they prolong the life and the service of the end-use product. And that is the accomplishment that you're looking for when you consider addition of any of these. In this last slide, I've listed contacts that are available. Eugene Valinsky. He's the professional that runs the equipment that I've tried to describe here for you today. If you have questions that pertain to UV testing and weathering, I would direct them to Eugene. I thank you for attending. I hope that in some small way this was beneficial and that you got something out of it. Thank you, and have a good day.